Europa has been lying to us. For decades, we looked at this moon and saw a frozen wasteland, a smooth ball of ice orbiting Jupiter, pretty in photographs, unremarkable in every way that should matter. Scientists talked about it politely, the way you talk about a colleague's vacation photos. Nice, interesting, moving on. But beneath that clean white shell, something has been happening. Something warm, something active, something that has no business existing on a moon this small, this cold, this far from the sun. And in the last 18 months, the James Webb Space Telescope has been quietly, methodically, pulling back the curtain on what Europa actually is. What it found is not what anyone predicted. Let's start with what we thought we knew, because that's where the cracks are widest. Europa is one of Jupiter's 4 Galilean moons, discovered in 1610 by Galileo himself. It's slightly smaller than our own moon, about 3,100 kilometers across. From the outside, it looks like a cracked egg. The surface is almost entirely water ice, crisscrossed with reddish-brown streaks and ridges that stretch for thousands of kilometers. And beneath that ice, there's an ocean. We've suspected that since the late 1990s, when NASA's Galileo spacecraft measured disruptions in Jupiter's magnetic field near Europa that could only be explained by a vast body of electrically conductive liquid beneath the surface. Salt water, an entire ocean of it, likely containing more water than every ocean on Earth combined, sealed under a shell of ice that could be anywhere from 10 to 30 kilometers thick. That ocean is what made Europa famous. Where there's liquid water, there's at least the possibility of life. Not a guarantee, not even a strong hint, just a door left slightly open. And for 20 years, that open door was all we had. We couldn't see through the ice, we couldn't taste the water, we couldn't measure what was dissolved in it, or whether anything was happening down there that would matter to biology. We were stuck outside, pressing our faces against frosted glass. James Webb changed that. Not by drilling through the ice, not by landing a probe, but by doing something deceptively simple. Staring at Europa's surface with the most sensitive infrared instruments ever built, and reading the chemical fingerprints of what's actually there. In September 2023, 2 independent research teams published results from Webb's near-infrared spectrograph, an instrument so precise it can identify molecules on a surface more than 600 million kilometers away. They were looking for one thing in particular: carbon dioxide. Not because carbon dioxide is exciting on its own, but because of what it would mean. Carbon dioxide on Europa's surface could come from 2 sources. It could be delivered by meteorite impacts or radiation from space, external sources that have nothing to do with the ocean below. Or it could come from inside, from the ocean itself, pushed upward through cracks in the ice and deposited on the surface. If the carbon dioxide came from below, it would mean the ocean contains carbon, and carbon is the backbone of every known form of life. Both teams found it. Carbon dioxide, concentrated in a specific region called Terra Regio, a geologically young area of disrupted terrain on Europa's trailing hemisphere. This wasn't a thin dusting scattered randomly by meteorite impacts. It was concentrated, localized, and sitting in exactly the kind of terrain that geological models predict would be refreshed by material welling up from below. The distribution pattern pointed downward, toward the ocean. Geronimo Villanueva, the lead author of one of the studies and a planetary scientist at NASA's Goddard Space Flight Center, put it plainly. The carbon dioxide was not arriving from outside. It was consistent with an internal origin. The ocean beneath Europa's ice contains dissolved carbon dioxide, and the geological churning of Terra Regio had brought traces of it to the surface, like a stain seeping through fabric. Carbon in a subsurface ocean is a prerequisite for the kind of chemistry that could, in theory, support life as we understand it. But Webb wasn't finished. In March 2024, a separate team used Webb to search for plume activity, jets of water vapor erupting from Europa's surface into space. The Hubble Space Telescope had reported possible plumes back in 2012 and again in 2016, but the detections were shaky, right at the edge of Hubble's capability. Some scientists believed them, others weren't convinced. Webb looked, and this time the answer was clearer. No large, persistent plumes were detected during the observation window. That might sound like a disappointment. It isn't. What it tells scientists is that Europa's plume activity, if it exists, is likely sporadic rather than constant. Enceladus, Saturn's tiny moon, fires geysers continuously from its south pole, fed by tidal forces kneading its interior like dough. Europa appears to be different. Its outbursts, if they happen, are intermittent, possibly triggered by specific tidal stresses as Jupiter's gravity flexes the moon's ice shell during its orbit. So where does the energy come from? Europa is far from the Sun. Solar heating is negligible at Jupiter's distance, roughly 780 million kilometers out. The surface temperature sits around -160 degrees Celsius. By every surface measurement, this moon should be frozen solid all the way through. The answer is Jupiter itself. Europa's orbit isn't perfectly circular. It's slightly elliptical, nudged into that shape by the gravitational tug-of-war between Jupiter and the other large moons, particularly Io and Ganymede. As Europa moves closer to and farther from Jupiter during each orbit, the planet's immense gravity squeezes and stretches the moon's interior. This is tidal heating, the same mechanism that turns Io into the most volcanically active body in the solar system. On Europa, the effect is subtler, but still powerful enough to keep an ocean liquid for billions of years beneath kilometers of ice. Think of it like flexing a rubber ball rapidly in your hands. The ball gets warm. Now imagine that ball is 3,100 kilometers wide, and the hand squeezing it belongs to the largest planet in the solar system. The energy generated by that constant flexing doesn't just maintain liquid water. It could drive hydrothermal activity on the ocean floor, hot vents where mineral-rich water meets cold ocean. Exactly the kind of environment where life originated on Earth nearly 4 billion years ago. Current estimates put Europa's ocean at somewhere between 60 and 150 kilometers deep. For context, the deepest point in Earth's oceans, the Mariana Trench, bottoms out at about 11 kilometers. Europa's ocean could be more than 10 times deeper, contained inside a moon smaller than ours. And at the bottom of all that water sits a rocky silicate floor, not a layer of high-pressure ice like you'd find inside Ganymede. Rock in direct contact with liquid water matters, because rock is where the minerals come from. Rock is where the chemistry starts. Webb's carbon dioxide discovery slots directly into this picture. If the ocean floor is hydrothermally active, and the ocean contains dissolved carbon and other compounds, then Europa has 3 of the 4 ingredients that astrobiologists consider necessary for life: liquid water, energy, and chemistry. The 4th is time, and Europa has had plenty of that. The ocean is estimated to have existed for billions of years. None of this means life is there. I want to be careful about that. Detecting carbon dioxide on the surface of an icy moon is not the same as finding a microbe. The gap between conditions that could support life and conditions that actually produced life is enormous, and we have exactly one data point for how life begins: Earth. Drawing conclusions from a sample size of 1 is bad science, no matter how exciting the results look. What Webb has done is narrow the possibilities. Before these observations, we knew Europa had water and energy. Now we know it has carbon too. Each confirmed ingredient shrinks the list of reasons to think life couldn't exist there. There's another piece of the Webb data that hasn't gotten as much attention: but matters enormously for what comes next. The research teams also searched for organic molecules, complex carbon-based compounds that serve as the building blocks of biological chemistry. The results were inconclusive. Webb detected hints of something, but the spectral signatures overlapped with other possible compounds, making a definitive identification impossible from this distance. That ambiguity isn't a failure. It's a signpost pointing directly at what the next generation of instruments needs to find. NASA's Europa Clipper launched in October 2024, carrying the most sophisticated suite of instruments ever sent to the outer solar system. Over the course of roughly 50 close flybys of Europa, some passing within just 25 kilometers of the surface, Clipper will map the ice shell in detail, measure its thickness, search for active plumes, analyze the composition of any ejected material, and probe the ocean's depth and salinity using radar and magnetometry. If Tara Regio is leaking ocean material to the surface, Clipper will taste it. If there are organics embedded in the ice, Clipper's mass spectrometer will identify them. Clipper won't arrive at Jupiter until 2030, but Webb's carbon dioxide finding sharpened its target list. Tara Regio, already a region of interest, is now a priority. The disrupted terrain, the carbon signature, the geological youth of the surface, all of it points to a place where the ocean is communicating with the surface. Clipper's job is to listen to that communication at close range and decode it. And it will have to work fast. Jupiter's radiation belt hits Europa with roughly 540 rem per day, enough to kill an unshielded human in hours. Clipper's electronics sit inside a titanium vault with walls nearly a centimeter thick, and even with that armor, the spacecraft can only survive brief passes near the surface before retreating to safer distances. 50 flybys instead of a stable orbit, because parking a spacecraft at Europa would fry its instruments within weeks. One of Clipper's 9 instruments is called SUDA, the Surface Dust Analyzer. Its job is to catch and analyze microscopic grains of ice and dust ejected from Europa's surface by micrometeorite impacts or plume activity. Each grain is essentially a tiny frozen sample of whatever material sits on or just below the surface. SUDA can determine the molecular composition of individual grains, which means it doesn't need a dramatic eruption to get useful data. Even the faint haze of particles kicked up by routine surface impacts is enough. One instrument, catching one grain, could change the entire conversation about what's in Europa's ocean. Clipper also carries an ice-penetrating radar called REASON, designed to map the internal structure of the ice shell down to a depth of about 30 kilometers. For years, theoretical models have predicted that pockets of liquid water could be trapped within the ice shell itself, sandwiched between the frozen surface and the deep ocean below. If those lakes exist, REASON should detect them as bright radar reflections at shallow depths, and it would mean Europa's habitable volume isn't limited to the deep ocean. There could be water, relatively close to the surface, in smaller reservoirs that might be more accessible to future landers. The chaotic terrain that covers roughly a quarter of Europa's surface, those zones where ice blocks have been jumbled, tilted, and refrozen at strange angles, has long been interpreted as evidence of subsurface activity destabilizing the ice from below. Warm ice or liquid water rises from depth, softens the overlying ice, and the surface collapses and refreezes in a disordered state. If that model is correct, then the carbon dioxide Webb detected at Tara Regio was carried upward relatively quickly by a convective process, cycling ocean chemistry toward the surface in geological bursts. That's a moon with an active internal circulation system, a moon that is, in a very real sense, alive geologically, even if it's not alive biologically. The radiation environment adds another layer, and it cuts both ways. Jupiter bombards Europa's surface with intense radiation, charged particles accelerated by the planet's enormous magnetic field. This radiation is strong enough to destroy complex organic molecules on the surface within decades. Any biosignature that reaches the surface from the ocean below would be chewed apart before we could detect it from orbit. But radiation also splits water ice and other surface molecules into fragments that recombine into new compounds, including hydrogen peroxide and molecular oxygen. Some models suggest that this radiation-produced oxygen could be cycled back down through the ice into the ocean below, where it would be available as a chemical energy source for any organisms that might exist there. Jupiter's radiation, which sterilizes the surface, might simultaneously be feeding the ocean. When I first read about that feedback loop, it stopped me cold. A planet that showers its moon with lethal radiation, and that radiation, filtered through 30 kilometers of ice, might arrive at the ocean as food. Europa doesn't play by intuitive rules. And Europa keeps delivering surprises beyond the carbon dioxide story. In late 2024, additional Webb observations revealed crystalline water ice features on Europa's surface that appeared fresher than expected. Fresh ice on a moon bombarded by constant radiation suggests recent resurfacing, material from below replacing the irradiated surface layer. The distribution of this fresh ice correlates with the same disrupted terrain where the carbon dioxide was found. Whatever is happening underneath the ice is still happening now. The chemistry Webb detected isn't a fossil, it's a bulletin. When researchers examined the spectral data more closely, they found that the carbon dioxide was mixed with other salts, specifically sodium chloride and magnesium sulfate. Table salt and Epsom salt, essentially. These are the same kinds of salts dissolved in Earth's oceans. Their presence in the same regions as the carbon dioxide paints a picture of a system in communication. The ocean talks to the ice. The ice eventually talks to the surface. And the surface, bathed in Jupiter's radiation, talks to space. Webb caught that conversation mid-sentence. The salt composition also feeds into models of the ocean's habitability. On Earth, hydrothermal vents on the ocean floor produce specific ratios of dissolved minerals depending on the temperature and chemistry of the rock they interact with. If Clipper can measure the precise salt ratios on Europa's surface and correlate them with what tidal heating models predict for seafloor conditions, scientists will be able to estimate the temperature and chemical environment of the ocean floor without ever touching it. They'll be reading the ocean's diary from the outside cover. Meanwhile, the European Space Agency's JUICE mission, which launched in April 2023, is on a slower trajectory to the Jupiter system. JUICE will focus primarily on Ganymede, but will conduct 2 flybys of Europa as well. Its instruments are complementary to Clipper's, meaning the 2 missions will cross-check each other's data. In planetary science, redundancy isn't waste. It's insurance against the kind of ambiguity that plagued the Hubble plume detections. There's a philosophical weight to all of this that I think gets lost in the technical details. For most of human history, the question of whether life exists beyond Earth was a matter for theologians and philosophers. It wasn't a scientific question, because we had no tools to investigate it. Then we built telescopes, we sent probes, we landed on Mars and found a cold desert, we mapped Venus and found a furnace. We catalogued the moons of the outer planets and mostly found cratered, airless rocks. Slowly, without anyone announcing it, the question shifted from philosophy to chemistry. Not, is there life out there, but are the ingredients there? That's a question you can answer with a spectrograph. That's a question Webb is answering right now. I keep coming back to Tara Regio because it's the geographic centerpiece of everything Webb has told us. It's relatively young, geologically speaking. Its surface has been reworked, broken apart, and reassembled by forces from below. The carbon dioxide sits there like a fingerprint left by the ocean, pressed into the ice by whatever upwelling process reshapes this terrain. If you wanted to design a landing site for a future Europa lander, a mission that could one day drill through the ice and sample what's underneath, Terra Regio would be on the shortlist. Webb effectively drew an X on the map. If you could somehow stand on Europa's surface and look up, the sky would be dominated by Jupiter. Not a dot, not a bright star, a wall. Jupiter would fill nearly 24 degrees of the sky, roughly 48 times the apparent size of the full moon as seen from Earth. It would hang there, banded in oranges and browns and whites, slowly rotating, the great red spot drifting across its face like a bruise that never heals. And you would feel, in a way that no photograph can convey, just how small Europa is, how completely it exists at the mercy of that enormous planet. The tides that keep the ocean liquid, the radiation that sterilizes the surface, the gravitational resonance that locks its orbit, all of it comes from Jupiter. Europa doesn't exist independently. It exists because Jupiter allows it to. And the conditions that make its ocean possible are the same conditions that make its surface lethal. That tension is the central fact of this moon's existence. What has changed, genuinely and measurably changed because of James Webb, is the strength of the case. Before 2023, Europa was a promising candidate in the search for habitable environments beyond Earth. After Webb's carbon dioxide detection, after the confirmation that the ocean's chemistry is reaching the surface, after the tightened constraints on plume activity and the sharpened target maps for Clipper, Europa has moved from promising to compelling. The difference between those two words is the difference between a hypothesis and a research program. We now have specific, testable predictions about what Clipper should find when it arrives in 2030. We have a named location where ocean material appears to be accessible. We have a chemical ingredient list that keeps growing. Somewhere in that tension, in the gap between a surface that destroys organic molecules and an ocean that might produce them, there could be an answer to the oldest question our species has ever asked. What would we find if we could actually get a sample of that ocean water? Not infer its composition from surface deposits, not model it from orbital data, but scoop up a vial of Europa's ocean and analyze it in a lab. If there are amino acids, if there are lipids, if there are any of the molecular signatures that life produces on Earth, even without cells, even without anything recognizably alive, it would be the most consequential discovery in the history of science. Not because it would prove life exists on Europa, but because it would prove that the chemistry of life is not unique to Earth, that the universe generates these building blocks wherever the conditions allow, that we are not a fluke. Europa didn't ask for our attention. It didn't erupt dramatically like Io, or parade its lakes and rivers in the open like Titan. It kept everything hidden under 30 kilometers of ice and let us guess. For 20 years, we guessed. And then Webb looked, carefully, patiently, with instruments built for exactly this kind of subtlety, and Europa finally gave us something real. The ice hasn't cracked yet, not for us. Clipper will get closer than anything we've ever sent. Suda will catch grains of ice no larger than a grain of sand and read them like letters from the deep. And one day, maybe in the 2040s, maybe later, a lander will touch down on that fractured terrain, melt through the ice, and lower an instrument into water that has never seen sunlight. Whatever it finds down there, whether it's barren saltwater or something stranger, will rewrite our understanding of where life can exist in the universe. For now, we wait. But for the first time, we're waiting with evidence, not just hope. Thanks for watching, and I'll see you in the next one.